Here we are for the review video of the action potential. So I've put everything together onto one slide, and I just want to go in chronological order. All right? So let's first remember, let me go to orange. Easier to see. That's kind of brown, it's kind of boring. Okay. We remember that at rest, the neuron has a negative charge on the inside relative to the outside. And of course, that's going to continue along the axon too, where the inside of the axon is negative relative to the outside. And for this one, I asked you to actually know the voltage. So the inside of the neuron is about negative 70 millivolts in charge. Cool. So remember, even though the nerve cell isn't doing anything, the fact that it has this resting charge means that it contains a form of potential energy. It's not doing anything at rest, but because it has this negative charge, it's a form of potential energy, so that when we want to, we can manipulate this and generate, in this case, an action potential or an electrical current. So how do we go from this resting membrane potential to an action potential or any kind of nerve impulse? And of course, we said all you had to do was open sodium channels, right? So all we have to do to go from resting to creating an electrical current is to open sodium channels, because a bunch of sodium rushes into the cell, turning the inside of the cell positive. And that quick switch from a negative charge to a positive charge generates a spark. And that spark is a current of electricity. We mentioned that there are two different types of nerve impulses. The graded potential is like a mini impulse. Many cells do it. Integrated potential, the spread of depolarization or the current can go in both directions. And that's what I'm showing you here, right? But also, as the current goes in both directions, it loses intensity. Eventually, it loses intensity until the current kind of peters out. Then we have an action potential. And in an action potential, this is a full-blown nerve impulse, which means that electrical current is going to travel the entire length of the axon, no matter how long the axon is. And in this instance, the current only goes in one direction, and the current maintains the same intensity throughout. The other thing I just didn't talk about for the graded potential was that it only has a local response, meaning that the impulse only travels a short distance before it stops, whereas an action potential travels a very long distance. All right, we said that in order to generate an action potential, and by the way, an action potential can really only happen in nerve cells. The graded potential happens in a lot of cells. These mini impulses is how a lot of cells communicate to each other. But the action potential only happens in nerve cells. I gotta take my sweatshirt off, folks. I'm getting all hot and bothered talking about this. Aren't you glad I don't actually take my clothes off when we're in lecture? To be clear, though, I have a t-shirt on underneath. Okay, a little too much personal information. All right, so if we're gonna have an action potential, we have to generate a graded potential first. And if this graded potential reaches a certain threshold, I think it's about negative 55 millivolts, but you don't have to know that number. The point is if that graded potential reaches a certain threshold of intensity, if it is intense enough, then it will trigger an action potential. But there's plenty of instances where we have lower intensity graded potentials that don't elicit an action potential. All right, so let's first talk about the steps of a graded potential. And we're going to see that these steps are very similar to the action potential. At rest, the inside of the cell is negative compared to the outside. That's how we started this. But now we are going to the magic phrase, open sodium channels. So here we have some sodium channels. And what's going to happen, remember we have more sodium on the outside of the membrane, more potassium on the inside. So when we suddenly open a bunch of sodium channels, sodium comes rushing in. And so much sodium comes rushing in quickly that the inside of the cell goes from -70 to +30. So much sodium comes in so quickly that the inside of the cell becomes positive. That quick change from -70 to +30, that is a 100 millivolt change. That quick change elicits a spark. That spark will then spread. So once we opened the sodium channels here, it gets a little messy here because I got so much going on. Next, we're going to open the sodium channels a little further down. Then we'll open the sodium channels here. And each time we open the sodium channels, sodium comes in and the inside of the cell becomes positive. So what basically happens is we have a situation where we have a spark because the sodium channel is open there, and in a graded potential, the depolarization wave spreads in both directions. So we have a spark there, and then we're going to do it again here. Spark, spark, right? Then we're going to do it again here. Spark, spark. It was the example of the wave like I gave in class, where one person stands up, that's the equivalent of the sodium channels opening and the inside becoming positive, creating a spark. And then when that one person stands up, in this case, the two people beside them stand up or depolarize, which makes the next people beside them stand up or depolarize. And it gives the illusion, the wave does, of something spreading, in this case to both sides. Now, of course, after the depolarization happens, that same area will close its sodium channels and the inside will return to negative. So just like we did in class with the example of the wave, someone stands up, open sodium channels, there's a spark, and they stand up long enough to cause the next person beside them to stand up. But once the next person beside them stands up, they sit down. They close the sodium channels, inside goes back to negative. And because it's a graded potential, that depolarization wave gets weaker the further off we get. And eventually it gets weaker until there's no longer depolarization happening. Cool. Now, as we said, if this reaches a certain threshold, then we will generate an action potential. So imagine, now we're down here, we had a graded potential, and let's say that it reached threshold. If that graded potential was intense enough and it reached threshold, then we would generate an action potential. The action potential has the same steps with only the addition of 1. And now, instead of being closer to where the nerve cell body meets the axon, now we're going to be traveling down the axon. So it's the same steps. What happens first is that sodium channels open. Sodium rushes in, turning the inside positive. That generates a spark. In an action potential, that depolarization wave is only going to spread in one direction. So after the first set of sodium channels open, then the next set of sodium channels open. Sodium comes in, inside becomes positive. And this spread of depolarization continues, and that little current spreads in one direction. This current will keep the same intensity the whole way. Just like we talked about the graded potential, after the first after the first sodium channel's open, and they stay open long enough for the next area to open its sodium channels, then we close the sodium channels, inside goes back to being negative. That is repolarization. Just like the wave. In an action potential, the wave is only going in one direction. You stand up, that's the equivalent of depolarizing the membrane. Sodium comes in, inside becomes positive. You stay standing up, you keep the sodium channels open long enough for the next area to stand up or open its sodium channels. But then once the next person besides you stands up, you sit down. And the added step of an action potential is that we actually, what color can I use? It's purple. In an action potential, we have this added phase of hyperpolarization, where now we're going to open more potassium channels. So not only have we closed sodium channels so they can no longer come in, but now we open potassium channels and potassium begins to flow out. So the inside of the cell becomes negative 90. So to review, when we depolarized, the inside went from negative 70 to positive 30. When we repolarized or closed the sodium channels, the inside of the cell returned to its same resting charge of negative 70. But in the case of an action potential, we open some potassium channels in addition to keeping the sodium channels closed, which makes the inside of the cell become even lower in voltage. The example we gave in class was that a person stands up for the wave, then sits down, but then slouches down in their chair. That would be an example of hyperpolarization. I didn't mention this in class, but the reason why we have hyperpolarization is because we want to make sure, well, there's two reasons. One reason we hyperpolarize is to make sure that we at least get back to resting. If we shoot for negative 90, we're going to be pretty darn sure to get to negative 70. And the other reason why we hyperpolarize the membrane is to make sure that each action potential is separate. And that goes back to the refractory periods we talked about, where while a nerve is busy making one action potential, there's a period of time where it can't make another action potential, and there's a period of time where it can, but it requires more stimulus. So the idea of the hyperpolarization is just to give the cell time to complete what had already started. All right, so we've talked about how it starts at rest, and then we've talked about a graded potential, and if that graded potential reaches a certain threshold, we will unleash a full-blown action potential. And then we end this story by talking about what happens when that action potential reaches the end of the axon. Because we know that at the end of the axon, there's a synapse or a space. This should be a review for you. So once that action potential gets to the end of the axon, calcium is going to come in to the end part of that axon, and that's going to trigger these neurotransmitters to be released into the synapse. We have many different neurotransmitters: acetylcholine, epinephrine, norepinephrine, dopamine, serotonin, etc. When a neurotransmitter gets to a postsynaptic membrane, it could be an organ, could be a muscle, which is an organ. When that neurotransmitter gets to the edge of the organ, that neurotransmitter will bind. So the neurotransmitter will bind to a receptor in that organ wall. Now, if that neurotransmitter binds to a sodium receptor, that means that sodium channels will open, and sodium, because we have more sodium on the outside, sodium is going to rush in, depolarizing the membrane and causing an excitatory response or an excitatory postsynaptic potential. It's the same step, folks. Actually, our bodies kind of boring. It uses the same things because it works so well. If that neurotransmitter binds to a sodium receptor, then sodium channels open, sodium rushes in. Anytime sodium rushes in, the inside of the cell becomes positive very quickly, and that is a form of a graded potential, which will excite. An example of a neurotransmitter that excites at an organ would be acetylcholine. When acetylcholine binds to a muscle membrane, it is actually binding to a sodium channel. Sodium rushes in, we generate another little mini impulse or graded potential, which travels the length of the muscle, goes deep into the muscle to the sarcoplasmic reticulum, causing it to release calcium, which goes deeper into the muscle to bind to actin. Shall I continue? But on the other hand, what if we have a neurotransmitter binding to a potassium channel? If this is the potassium channel will open and potassium is going to flow out. And if the inside of the cell, of the organ membrane, if the inside of the organ all of a sudden loses a lot of positive potassium, it will become even more negative. And that is a way of inhibiting that postsynaptic potential, or that postsynaptic membrane, which is a form of an inhibitory postsynaptic potential. So I give you some examples in the PowerPoint. For example, I believe it's dopamine. In some areas, when dopamine binds to a postsynaptic membrane, it has an inhibitory effect. You can imagine this like a green light, red light situation. These neurotransmitters, I just realized I misspelled neurotransmitter, forgot an N. Please forgive me. These neurotransmitters either act to excite the membrane or give it a green light to go, but we also sometimes need to deliver a neurotransmitter to inhibit a membrane, tell it to stop. Because if we keep telling it to go, we're never going to tell it to stop. So it's equally as important sometimes that we're able to deliver a message to stop or inhibit red light. Hope this helps. I've also posted some videos online for you. Good luck. Oh, that's the wrong way to do it, Dr. J.